and share my screen. And when I share my screen, I'd like to look at the course home in my math. Oh, wait a minute. Before I do that, I always forget to open the chat first. And now the chat's disappeared anyways. Oh dear. If somebody posts a question in the chat, could you guys let me know? Because when I'm sharing my screen, that doesn't show up for me. Does it show up for you folks or no? Let's see.
I see it.
Okay, now I got it. I got it. I got it. Oh, no, I don't. It disappeared. Okay, I'm giving up. Please notice that I added something in my math lab for today. I wanted to give a quiz today, and I thought that I would try to give it during class time in my math lab, but then I thought it would probably be time consuming for everybody to have to go and open their own My Math Lab. And so I've got it. You can only take it once, and it's due, please notice that it's due by before midnight tonight. It's timed, it's set up so that you have 15 minutes. I need to apologize. People who had given me a form already saying that you get extra time. I did not add that yet. I will go through and do that as soon as class is over. Also, homework 1 is to be done by the end of the day today. Did anybody have any questions in homework 1 that they'd like to look at before we start looking at today's notes? I'm thinking in a couple of my classes, I did get Ask My Professor questions, but I don't believe that I can remember right now any from Math 106. So I'm going to go on the assumption that everything's fine. Can I also go on the assumption that everybody is active now in my math lab, in my lab's math? I know I did the couple questions that I did get were people asking for a course ID, saying that they had a little bit of a problem getting in. And I have to apologize. Those types of problems, I can help you with the math problems. I can't help you with the technology problems. If you have any of those technology problems, on the course page for Blackboard down at the bottom, I've got a link here for my lab support. When I have technology problems with them, I kind of just close the site, walk away and come back in 5 minutes, and usually in 5 minutes it works. I don't know what's up with that, but if that, like, pull the plug 5 minutes, outlook on fixing technological problems does not work, then use that link to get help from them. Anybody want to look at anything from any of the homework, or anybody have any My Math Lab problems that they need to discuss? This is when I hate Zoom, because usually if we're in a classroom, I can kind of just scan the room and look at everybody, and I can tell by facial expressions whether we're good or not. And that's the one I miss seeing you folks so much. But no questions then today. Today's September 8th. We're going to start by looking at the terms finite and infinite. There's a little bit of that in that homework that is due today. We're also going to start looking at the idea of subsets, just both regular subsets and proper subsets. The quiz needs to be done by 11:59 today. Homework 1 is due by the same time tonight. Homework 2.2 is due by Thursday. We'll stop a couple minutes before class and make sure that we're far enough along that that due date is reasonable. But if I remember correctly, when last we met, we finished by talking about the difference between equal sets and equivalent sets. I don't think this section we have done any discussion the idea of what it means for a set to be finite. Had we talked about that term finite yet?
No.
No?
No.
Okay. A set is finite. If cardinality is a natural number.
And do natural numbers, that doesn't include 0, right?
Right, right. Although I guess the empty set is considered finite. So maybe we should technically change that natural number to whole numbers. Thank you. Although I think Mr. Blitzer in his infinite wisdom defines it as a natural number, not a whole number. Huh. First time somebody asked that. There in all of the years of my teaching this. Very cool. Now you've got me thinking. But help, what does it mean when, can anybody remember from last class what we meant when we talked about the cardinality of a set?
How many elements are inside the set, like the number of elements?
Beautiful, it's the number of elements. And so if the number of elements is a whole number, a counting number, then that means that we can count how many things in there and stop. So we can count the elements. So let's look at a couple of examples. Let's say S is the set of students that are registered at Niagara County Community College. Would that be finite? Would we count the number of students enrolled in the college?
Yes.
Yes, so that set is finite. Let's say T is the set of all X such that X is less than or equal to 1,000 and X is a natural number. Could we count how many numbers there are less than or equal to 1,000?
Yes.
Yes, so that's also a finite set. Let's say V is the set of all X such that X is greater than 1,000 and X is a natural number. Can we count all of the numbers bigger than 1,000? If I started counting 1,001, 1,002, 1,003 and kept counting, would I ever end? If I want, no. So this is an example of a set that's not finite. And not finite sounds a little peculiar. Instead of not finite, we call those infinite. So an infinite set, it's a set that's not finite. We cannot count all the elements. It's considered a set that never ends. There are a couple in the homework, you might run into a couple of very large sets that some people might view as, that's, some people see it as shades of gray, but Mr. Blitzer does not consider them infinite. So let's say, for example, I say G is the set of blades of grass in my lawn. And that set is actually considered finite because if I were to freeze at an instant in time, I could, in theory, go out and count all the grass in my lawn. It would take a very, 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 very long time, but I could count them. Another example that I see in different textbooks is the grains of sand on a beach. And I guess technically, if you wanted to, you could count all of the grains of sand on a beach, and it would, you would eventually run out of grains to count. I know that one's one that I've had people debate me on, because if you picture the water coming in and out, that's not a fixed number. But if we were to just like freeze it an instant in time, then it wouldn't be considered a finite set.
So just because something is considered finite doesn't mean it has to be realistic.
Yeah. Yeah. I promise I won't give you anything that extreme of an example of a test or quiz. I'd like to look at no two infinite sets. And the first infinite set I'd like to look at is the set of natural numbers. And is everybody comfortable with the idea that the natural numbers would be infinite? I could continue counting them for the rest of my life. It would never end.
Yeah.
I'd like to also consider another set, E. And E is going to be the even naturals. And so that would be the set 2, 4, 6, 8, 10. And is everybody comfortable with the idea that both of those sets are infinite, the even numbers are infinite? I'd like to ask, which set do you think is bigger? Which set do you think has more elements?
I think it's the regular natural numbers, because I have heard things like some infinities are bigger than others, which is really weird to think about. But
yeah, well, actually, most people intrinsically think that the natural numbers are larger than the even numbers, because it's all the even numbers plus all the odd numbers. But what happens is these sets are considered equivalent. Now, wait a minute, how can they be equivalent? First of all, are we in agreement that these sets do not have a cardinality? And so we had said one way of telling if two sets are equivalent are if they have the same cardinality. But these don't have a cardinality, so we can't use that definition. When we talked about equivalent sets last class, the big fancy definition says we can construct a one-to-one correspondence between the elements of the sets, so that every element of the set corresponds to the elements of the second set. Every element of the second set corresponds to an element of the first set. And couldn't I go through and start pairing off each of the natural numbers with its double, or each of the even numbers with its half? And couldn't I go through and for any even number come up with a natural number, and for every natural number come up with an even number that it would match with? So we can say here that there is a one-to-one correspondence.
Well, wouldn't the even numbers run out faster than just like the natural numbers? So
Give me, if I had an even number, a huge one, let's say 1 million, wouldn't that pair to half of it, 500,000? And any even number that I come up with, couldn't I pair it with a natural number? And every natural number that I came up with, let's say I have 1,000,001, couldn't I pair it with an even number? It's double, 2,000,002. And so there would be a partner for every natural number in the even numbers. There'd be a partner for every even number in the natural numbers. And so that's that. And the only reason I bring up this example is because we had talked about that one-to-one correspondence for sets that didn't have cardinality. This is just an interesting example of that. I didn't bring this up in the other section. I'm not going to hold you guys accountable, but I heard somebody talk about different types of infinity. And so the cardinality of the natural numbers is considered, it's a funny looking symbol like this. It's called aleph naught. And it's a type of infinity. In a course that I took, getting my bachelor's in math, that spent a lot of time on set theory and infinity, it's considered countably infinite. As opposed to something like the rational numbers, the fractions, between any two fractions, there's an infinite number of numbers. And so that would be a different type of infinity. So, and again, that aleph naught, I'm not going to hold you accountable for, but it goes on that idea that there are different types of infinity. So that's the last thing, that idea of finite versus infinite. And again, this is the equivalence of those is, you know, beyond what you're going to see in the homework quizzes. I just thought it's something interesting, and in case anybody wanted to know why we needed that alternate definition of equivalent sets. Let's go on and let's start looking at that next section, 2.2, unless somebody has a question. If not, section 2.2 deals with the idea of subsets. When we talk about subsets, what happens is we start to compare sets. And so if A and B are sets, so when I start talking about the idea of subsets, I need two sets. We'll say that B is a subset of A. If every element of B is also an element of A. Every element of B is also an element of A.
But does that also mean that if something is a subset that it's equivalent?
No, not necessarily. Sometimes they are, but sometimes they're not. Let's just look at the notation first. If I write B is a subset of A, this is read as B is a subset of A. So, as I look at that symbol for subset, the shape of the symbol reminds me a little bit of what it means. As I look at the top of that symbol, does anybody else see that as a funny looking C? And so the fact that it's the funny looking C, it tells me that B is contained, and that should be an uppercase B, I apologize. B is contained in A. And then that little line underneath, bring that little line underneath. Does it remind anybody of the less than or equal to? Like, it's okay if they're equal. So B is contained in A, and it's okay if they're equal. And we say that B is a subset of A. Every element of B is also an element of A. So let's look at a few examples. Let's start looking at an example of a set. by description. Before I do that, am I writing too fast? Does anybody need me to take a minute? Stop.
We're okay.
So if it is a subset, does that mean that it is equal?
It can be, but it does not have to be.
Okay.
Okay, so let's look at an example. Let's say that S is the set of students in class today. Let's say M is the set of men in class today. And let's say W is the set of women in class today. Can I say that M is a subset of S? Is every man participating in this Zoom meeting, every man in class today, participating in this Zoom meeting, a student in class today?
Yes.
Now, are they equal? Are all of the students men?
No.
No. So this example, they're not equal. Could I say that S is a subset of M? Is everybody in class today a man?
No.
No. So here we'd say it's not a subset. And that symbol for not a subset is the subset symbol with a slash through it. But I say that M is a subset of M. Is every man in class today a man in class today?
Yeah.
Yes. And is everybody all right? That would be an example where the two sets can be equal.
Yeah.
Could I say that W is a subset of S? Is everybody, woman in class today, a student in class today?
Not necessarily, if we count you.
I guess technically, but I'm talking about women students, so.
Okay, then yes.
Okay, would M be a subset of W? Is every
No.
man in class? No, I don't think all the men in class identify as women. Now, the next one's a little dicey. But before I go on, can we look at these two that are not subsets? Is everybody all right that S is not a subset of M because there's students in class that are not men? Can we say that M is not a subset of W because there are things in that set, there are men in class that do not identify as women? So I want to look at this set here. Can anybody remember what that symbol means?
That's empty set.
That's the empty set. There's nothing in there. Is the empty set a subset of S?
No,
No.
Why not?
because that felt like the right answer.
They're
All right.
because we're in the set listed.
But is there anything in the, somebody raised their hand. Okay. Robert, question?
Hi, sorry. Is that not something we do in here? We don't raise our hands. We just.
Yeah, just talk. That's fine.
Okay. I do think that the empty set is a subset of S, and the simple reason for that is that we can technically find emptiness in S. If
Right.
everything in the, I'm sorry.
You're right.
All right. Should I go on?
Sure.
Yeah. Technically, we can find emptiness in S because where was I going with this? I'm sorry. Give me a moment.
I'm sorry, I didn't mean to interrupt.
Oh, no, it's all right. I'm sorry. I'm still tired. If everything in the subset can be found in the set, then it means that the subset is a subset of the set. So as a rule, I guess we can all remember this as a rule, empty sets are subsets of the set.
Empty set is a subset of every set. Because
Yeah.
going up here, why was S not a subset of M? Because there were students that were not men. There was something in here that was not in there. There is nothing in the empty set that's not in class. Just think about it. There could be some really, really sad day. I'm crying thinking about it, where nobody shows up for class. And so that day, the class would be the empty set, but it would still be class for that day. So we're going to say that the empty set is a subset of every set.
Like ever?
Yep. Because if it doesn't have anything in it, it doesn't have any extra elements that are not in the other set. So let's look at another example, an example where we can list all the elements of the set. I'm going to change pages. Is everybody all right if I insert a new page?
Mm-hmm.
Yep.
So this time, let's say A is the set with C, A, R. Let's say B is the set with C, A, R, T. And let's say C is the set with C, A, T. Is A a subset of B?
No.
Yes.
Is everything in set A, C, A, and R, also in set B, C, A, R, T?
Yeah.
Is B a subset of A? Is every letter in set B, C, A, R, T, do they all show up in set A?
No.
No. So please notice with that subset symbol, the order in which you put the sets is important. Is C a subset of B?
Yes.
Yes. Is C a subset of A?
No.
No. C has a T in it, A does not. Is the letter T a subset of set B?
Yes.
I see T in B, but in order to be a subset, it has to be a set. Is the letter T all by itself a set?
No.
No.
No, it's not a set.
I think that the letter T is an element of set B, but it's not a set of set B.
Beautiful. And that's the way we should write it. T is an element of the set and not a subset. I could have written it, the set containing T, and then it would be a subset. But in order to use that subset symbol, you need to be comparing two sets. You can't be comparing an element to a set. To be a subset, they have to both be sets. So far, so good. If so, we've talked about general subsets. There's a particular type of subset you sometimes hear of, and that's a proper set. Proper subset. If A and B are sets, we say that B is a proper subset of A, and that's written B is a proper subset of A. So that over here, the C without the line underneath it means proper subset. And I'm guessing that I'm speaking to a group of intelligent college students. I'm guessing that comparing that symbol to the regular subset symbol, does anybody notice what's different?
The line.
The line isn't there. The equal sign isn't there. So we say that B is a proper subset of A if B is a subset of A, but B cannot equal A. B is a subset of A, but B is not equal to A.
And that rule applies every time you use this symbol, every time we're talking about a proper subset.
Right. With proper subsets, that line isn't underneath there, so they cannot be equal. So the first set is contained in the second, but the two sets are not equal. So if I go back to the example that we just had, where A was the set C, A, R, we could say that A is a subset of A, but A is not a proper subset of A because it's equal to itself.
So proper subsets can never be equal. That's fair to say?
Mm-hmm. And so, you know how we had said that the empty set is a subset of every set?
Yes.
The empty subset is not a proper subset of the empty set because they're the same. So the empty set is a subset of every set. It's a proper subset of every non-empty set, but it's not a proper subset of itself. How crazy is that? So the empty set is a proper subset of every set except the empty set. And so we're going to spend, in the homework too, you're going to have a little bit of time comparing two sets. Is one a subset of the other? Are all the elements of the first set also elements of the second set? The other thing you're going to see in that second homework deals with counting the number of subsets a set can have. So let's go through and let's look at counting how many subsets and proper subsets a set can have. And we're going to find out that there's a formula that relates the number of subsets a set can have to its cardinality. And I'd like to take a minute and look at a few examples before I give you the formula, because I don't know about you guys, but in order for me to be able to remember a formula, it has to make sense. And so I'd like to look at some examples to kind of give you an idea as to why the formula is. So let's start for the first example. Let's start with the empty set. How many things are in the empty set?
0.
0. If I ask how many subsets the empty set has, it would only be one. It would be itself. But if I ask how many proper subsets it has, Does the empty set have any proper subsets?
Wouldn't it be like infinite?
Would it? Can you give me a subset of a proper subset of the empty set? Can you give me I don't, the only subset that it has is the empty set. So, next example, I want to look at a set A. And I'm gonna just put the letter A in there. What's the cardinality of A? How many things are in that set?
One.
One. If I asked you to list its subsets, what would be a subset of that set? We could have A, and we could have an empty set. So doesn't that set have two subsets?
Yeah.
Of those two subsets, how many are proper?
One.
One, because we can't have the set itself. Let's look at another set. For lack of originality, I'm going to call it B. And this time I want to put in the letters A and B. What's the cardinality of that set? How many things are in there? Two. If I asked you to list all of the subsets of that set, what would we have?
4.
We could have, I know somebody just told me there are 4.
Yeah.
Want to list them so that everybody else sees why there's 4?
Sure. You take the set itself. That's A comma B. So every set is a subset of itself. That's a rule. And then you have set A, that's another one. And then you have set B, that's another subset. And then you have the empty set, which is the 4th subset.
Everybody in agreement? We got 4 subsets there?
Yep.
Now, of those 4, how many are proper?
3.
3, because when we count the proper, we'd eliminate the set itself. One more, and I bet you guys can guess what I'm putting in this third set, A, B, C. What's its cardinality? How many things are in set C?
3.
3. Now, if I wanted to list the subsets, we'd have the set itself, A, B, C. We'd have the empty set. What other subsets would this have?
Set A.
Just A, just B, just C. Any others?
A and B,
A and B,
B and C, A and C,
B and C, A and C. Any others?
The empty set?
All
I
right.
think we started with the empty set. You're right.
I think that's all because the number of sets that should be 8. Do we have 8?
I think we have 1, 2, 3, 4, 5, 6, 7, 8, 8. And of those, how many are proper?
7.
7.
So now I want everybody to look at what we did. If a set had no elements, it had 1 subset. 1 element, it had 2. 2 elements, it had 4. 3 elements, it had 8. Every time we added an element, what happened to the number of subsets?
Expand.
It expanded, but by
It
how
doubled.
much? Didn't it double each time?
yes.
Yes. And so that's the reason I go through and generate this list every semester, because I think it's very clear looking at this list that every time we add an element, the number of subsets doubles. Yes? And so that gives me a formula for the number of subsets of a set is given by the formula. Now, it doubled. So does it make sense that this formula has to involve the number 2?
Yes.
And what happens is this formula is 2 to a power, 2 to the n, where n is the cardinality of the set. So let's take that idea and work backwards, compare it to the list that we had. Is 8 2 to the third? 2 times 2 times 2 is 8. Is 4 2 to the second?
Yep.
Yeah.
Yeah.
Is 2 2 to the first?
Yes.
Now, the next one I'm not sure everybody's familiar with, but we're going to say that 1 is equal to 2 to the 0 power. Have you folks all seen in an algebra class somewhere that any number with an exponent of 0 will always equal 1? One exception though, 0 to the 0 is undefined. But if anybody's got a calculator, one of them, if you take any number and raise it to the 0 power, you will always get 1. Now, I'd like to compare the number of subsets to the number of proper subsets. 8, 7, 4, 3, 2, 1. Do you notice that the number of proper subsets is always 1 less than the number of subsets? So the number of proper subsets is 2 to the n, take away 1. So that formula is useful if you're asked to list how many subsets a set has. It gives you an idea as to how many things ought to be in your list. But let's look at a couple other examples. Let's say that V is the set of vowels in the alphabet. What's the cardinality of V? How many vowels did we say we have? A, E,
5.
5. Beautiful. So the number of subsets of B, number of subsets of, sorry, I misspoke, V, not B, is 2 to the 5th. And so when we take 2 to the 5th power, 2, 4, 8, 16, 32. At which point, this is one of those places where you might want to use a calculator. On their calculator, is everybody comfortable with exponents? Does everybody know how to raise a number to a power on their calculator?
You just times it by itself, right?
Oh, if you're a glutton for punishment, but let's finish this question and then we'll look at it. So the number of proper subsets would be 1 less than that, or 31. Let's look at C is the set of consonants. The cardinality of C, well, the rest of the alphabet would be consonants, so that would be 21. And so if I look for the number of subsets, that would be 2 to the 21st power. And you see how this time I wouldn't want to go 2 times 2 times 2 times 2 times 2 times 25 times. So I'm going to stop sharing for a minute. And I'm going to hold my calculator up in front of the camera. Can everybody see it all right?
Yep.
So I'm going to type in the number 2. And then as I look at my calculator going down the, yikes, I'm getting my hands confused, left-hand side. On this model, does everybody see this button here that's like an arrow up, a caret up?
Mhm.
I'm going to use caret up, 2 to the, and then I'm going to type in 21st. And so, do you see how what I have in my display is 2 caret up 21?
Yeah.
And that's raising it to the 21st power.
Okay.
2 to the 21st power is, holy granoli, 2,097,152.
Mhm.
Some people might not have that caret up button. If you don't have that caret up button, you're going to have a little button somewhere on your calculator that's something like y to the x or x to the y. But that gives me, let's see, let's go back to sharing. That gives me 2,097,152. So now we know how many there are. We can start listing them. Do you guys want to list them?
No, thank you.
No, I'm being silly with that one. Of that, how many of those subsets are proper? 2,097,151. To get the number of proper subsets, we always just go down by 1. So far, so good?
Yep.
Let's look at another one. Let's have S be defined as the set of all x such that x is less than or equal to 100 and x is a natural number. What's the cardinality of S? How many numbers are there less than or equal to 100?
100.
100. We all in agreement?
Yes.
If I ask for the number of subsets of S, that would be 2 to the 100th power. So I'm going to grab my handy dandy calculating machine, clear that last one out, and raise 2 caret up 100. And wow, is anybody else getting something really weird on their calculator like 1.2676506? At which point, why is that giving me a crazy decimal? I'm counting. I should be getting a counting number and not a decimal. In fine print, mine has something like times 10 to the 30th. Some people might have E30 after that number. And when your calculator gives you a display like that, it means that your number is too big for the calculator display, and it's putting it in scientific notation. And so it means that it's 1.2676506 times 10 to the 30th. And so you would have to hike that decimal point over 30 places. You're probably not going to see any quite that big in the homework or on a test or quiz, but I did want to give you a heads up that if your calculator gives you display like that, let me real quick show you on mine. What that's doing is that's throwing your number in scientific notation. And so if you're expecting a very large number and you get a decimal instead, a small decimal, 1 point something, 2 point something, an answer smaller than 10, look at the back side of your calculator display. It should be a power of 10. It should be sending that number into scientific notation. I'm not sure if you've seen that before, but does that make sense? Has everybody at least heard of scientific notation before?
Yep.
Great. Really, that's all there is in chapter 2, section 2. A bit of time is spent on making sure everybody knows the difference between a subset and a proper subset. Subset, everything from the first set is in the second. Proper subset, they cannot be equal. Regular subset, it's okay if they're equal. And the little line underneath the subset symbol tells me that. I look at that almost like the difference between less than and less than or equal to. The other thing, just remember that the number of subsets is always a power of 2, and for proper subsets, you take 1 away. If that's all right, we're going to go on and do a little bit of introduction into section 2.3. And 2.3 deals with set operations. And if I'm not mistaken, I remember somebody asking last week when it came to things like sets, if you ever doing anything like adding or subtracting or multiplying or dividing. And I said, no, but we will have distinct operations that we do on sets. Before we start doing operations on sets, though, we're going to look at something that's called a Venn diagram. And here I want to give you a heads up. I apologize, I cannot draw. Because I cannot draw, I do not take off for artistic merit. When I talk about a Venn diagram, we're going to be drawing. A Venn diagram is a diagram that shows the relationship between sets. Before I draw a Venn diagram, there's a couple of terms that I need to define. And the first one is the universal set. And the universal set is the set of everything being considered. And most often, the universal set is shown with an uppercase U, but this uppercase U usually has kind of a tiny little bit of a tail on it, almost like an italicized uppercase U. It's like the universe, the world that I'm considering. The universal set in a Venn diagram is usually represented by a rectangle, and somewhere in one of the corners there's usually a U. So for example, if I look at that M is the set of men in class, and S is the set of students in class. Here, the students in class would be my universal set. And the men in class is a subset of the students in class. And so I show that as being contained in the universal set. So subsets of the universal set are are shown as loops inside the universal set. And so let's look at another example. Let's let our universal set be the alphabet. Let's have V be the set of vowels. And if I were to draw a Venn diagram, inside that box, I'm going to picture having listed all of the letters of the alphabet. But I'm going to take all of the vowels and put them inside that loop. So this would be the vowels. If the vowels are inside the loop, what would be outside the loop?
Consonants.
Consonants. Outside the loop would be the letters that are not vowels. All of the letters, all of the elements of my universal set that are not inside that set. And that takes us to our next definition, which is that of the complement of a set. And the complement of a set is a set, and it's, if S is a set, S prime, it almost looks like a little apostrophe after the S, is the complement of S. And it's the set of all the elements of the universe that are not inside my set S. Oh Lord, I can't spell today. Sorry about that, folks. That are not elements of the set S. And so a picture showing this relationship, if this is my universal set, and this is my set S inside the loop, the rest of stuff outside the loop would be what's in S complement. Everybody with me, or do you want me to wait a second for catching up? Or are we all right?
Okay.
People who speak are good, silent majority. Are you guys all right?
You're good.
All good.
Okay, great. Then let's look at an example. Let's have our universal set be the numbers 1, 2, 3, 4, 5. Let's have a set A be the numbers 1, 3, and 5. And let's draw a Venn diagram. And when I draw a Venn diagram, I like to think of it as you start from the inside and work your way out. You start in the innermost section. So what does that mean?
The circle?
We're going to start with the elements inside the circle. So over here, this circle is set A. What's inside of A? 1, 3, 5. When I put the elements in the set, I can put them anywhere I want in the set. They just have to be in the loop. Now, because the loop is inside the universe, is everybody all right? I've already got 1, 3, and 5 in my universe. I'm not going to rewrite them. They're there. Is there anything in the universe that is not in set A?
4.
4. Anything else?
2.
2. And so then I'll work my way out and take the elements that are not in my set and put them in the rest of my universe. So again, A is 1, 3, 5. What would A complement be?
2 and 4.
2 and 4. And when we draw a Venn diagram, we start with the innermost and then work our way out. So far, so good. So then, next thing we're going to look at is for Venn diagrams with 2 sets. And if I were a glutton for punishment, I'd be drawing a whole bunch of different cases. I could consider the case, first case, where the sets are disjoint. Elements in common. And so if that was my universal set and I wanted to draw 2 sets with nothing in common, couldn't I just put 2 separate loops in there?
Yeah.
Next case, where one set is a subset of the other. And if one subset was a subset of the other, couldn't I draw it inside the other one? Kind of looks like a donut. In the third case, where the 2 sets have some elements in common, well, I'd start with my universal set. I'd have my first set, and if the 2 sets have some elements in common, they'd have some sort of overlap, wouldn't they?
Yes.
And what we're going to see is that this Venn diagram is the one that we're going to always use for 2 sets. Because as I look at that Venn diagram, it gives me 4 regions. And so I'll have set A, set B, and my universal set. And when I look at those regions, usually the regions are labeled with Roman numerals. And so this would be region 1, this would be region 2, this would be region 3, and this would be region 4. Region 1 would be what's only in A, only elements of A. Region 3 would be elements that are only in B. And so if you look at the first case with the 2 disjoint sets, region 1 would be full, region 2 would be, I'm sorry, region 3 would be full, region 2 would be empty. Region 2 would be the regions of common to both. And if I had that second case, all of B would be in here. Everything in B would be in A, and region 3 would be empty. And then region 4 would be the complements of both, outside of both. And so if things are outside of both sets, there will only be elements in region 4. So, for example, let's have, say we're given a Venn diagram. And actually, I'm looking at my clock, and I've got that there are 3 minutes left in class. So rather than going any further with this, because this is from homework 3, I'm going to stop here so that I'm not racing to go further. Anybody have questions on anything from today? And again, we'll spend a lot more time on these Venn diagrams on Thursday.
My only question is just about the quiz you were talking about earlier.
Right, that's where I was going next. What do you want to know about the quiz?
I can just wait and see if you answer my question if you want.
No, go ahead.
I was just gonna say, we access it through the same way we access everything else, or?
You're gonna, in order to access that quiz, what you're gonna do is you're gonna go into Blackboard. And in Blackboard, you're going to go to My Math Lab. In My Math Lab, you're going to go to All Assignments. And in All Assignments, the quiz on set definitions is there. I know that previously I had said that with quizzes, I needed to see all of your work, but I think the nature of the questions that are being asked here, you do not need to submit work. It's real short, there's 5 questions. Just put your answers in My Math Lab, okay?
Okay.
I will look at them before we meet on Thursday. And if there's something that's painfully, obviously a typographical error, I will go through and give partial credit for that. But with these types of problems, I don't really think there's a need to necessarily show your work. All right? So don't worry about submitting work for this one. All right?
Okay.
Sure.
Did I answer the question?
Yes.
Okay, great. Then,
Well,
go ahead.
I'm sorry, real quick. Will the quiz cover any material from 2.3?
It will only cover material from 2.1.
Okay, thank you.
Okay, I promise that I will try hard not to quiz you on something until you've had the opportunity to try the homework. Next class, ask questions on the homework so that questions can be clarified before I quiz you on it. All right?
Thank you very much.
Otherwise, the homework isn't doing its job. The homework is to get you comfortable with the stuff before it counts as a test or quiz. All right. So, have a great rest of your day, and we'll see you guys all on Thursday. If there's anybody who showed up late and wants me to count you as being president, hang on at the end of the meeting and let me know. Let me stop sharing my screen and let me turn the recording off.